Well, I'm working in nuclear astrophysics, so we're basically trying to understand the nuclear processes that happen in the cosmos that create the elements. We're asking questions like, what is the origin of uranium or gold in the universe? We're trying to understand supernovae, other stellar explosions. And we pretty much do that by kind of restaging the nuclear physics in the laboratory here at the cyclotron. Yeah, GINA is a joint institute for nuclear astrophysics, and we're really excited that we have that here. MSU and the cyclotron is one of the core institutions of GINA, and it has been founded to basically bridge astrophysics and nuclear physics and to kind of enable this interdisciplinary research. Because these are different fields and people don't always communicate with each other. And we decided we want to take a different approach, and we want to basically look what are the problems, what are the open questions. Here's something we don't understand, and then we want to see, okay, this is what the astronomers have to do, this is what the nuclear physicists have to do, and then we work together on the problem. And it works very nicely here at MSU. We kind of have a GINA microcosmos here between the astronomy department and the cyclotron. And then there are all the other GINA institutions, the University of Notre Dame, University of Chicago, and then a lot of associated places, basically all over the world, in Europe as well as in the US. And a lot of people with very different expertise come together, and I think it's also great for the students. They're fully part of that enterprise. They can travel to other institutions, and if they're working on a nuclear experiment, they can learn something about astrophysics. Well, usually experiments tend to work here. They have to. But actually we had an interesting experiment some time ago trying to measure the half-life of nickel-78. Which is important in the R process, which is one of the processes in supernovae that creates heavy elements, and it's a very important nucleus, and lots of people have tried to study it, and we thought we have a shot at the cyclotron. And the experiment was part of a movie actually that we were trying to do about nuclear astrophysics. So another professor, he had some idea to do such a movie, and so there was a camera crew, and they were trying to film how we do an experiment, and all they basically saw was things were breaking down, nothing worked. The students looked really depressed, and and we told them they have to come back the next day, and they came back, and it was the same thing. Nothing worked. We were just running around like mad. And then finally, when they left, things started coming in, and things come together, and it was kind of fun to see how they managed in the end to. If you look at the movie, it actually looks like everything worked very well, but they just cut it together in an intelligent way. But that was a nice experiment. Well, what gets me excited is that connection between nuclear physics and astrophysics, and how something that's just a few femtometers and lives for maybe 100 milliseconds, an exotic nucleus, how that thing can basically shape how an entire supernova looks like, and how much uranium we find today in the sun. Well, because of GINA, that's one thing. But also the lab itself is a very nice environment. It's one of the leading nuclear physics labs in the world, and I think you'll get a really excellent education here. It's a large laboratory, and I always tell students it's important that you visit the place, that you look at things, that you look at the people you're going to work with, and that you make sure it's really interesting, it's really what you want to do. And not everybody likes a large laboratory. Some people prefer smaller ones, but so you have to look out for that. But if you like to work in an interesting large place and international collaborations, and then I think this is a good place. And also our experiments are still at a scale where an individual student can have a lot of impact. Individual students can basically be the project leaders. They can decide, I want to have that detector there, and then they still have to convince a few people that's a good idea. But you really can steer your experiments, and you'll be involved in design of the apparatus and running the experiment, analyzing the data, and the interpretation. And I think this is a very nice way to learn a lot of different things. I got pretty lucky, I think. Things turned out to work out all right, but it just happened. So I think the important thing is that you really look what is it that interests you, and that you go after that. In science, you can't just do a job. You really have to be committed, and you really have to be interested in finding the answers to the science questions.
NSCL is a world-leading laboratory for rare isotope research and nuclear science education. Operation of NSCL as a national user facility is supported by the Experimental Nuclear Physics Program of the National Science Foundation.